In this video I'm looking at sideband noise generated by capacitors. I have this tube oscillator that you have seen in the previous videos, 3 dB of fixed attenuation, and then this stepped attenuator from Hewlett-Packard. And then the signal goes to this box, right now to the straight through wire, and I will put various things here. And then this output is intended to go here. So this is a directional coupler, and after that the selective load and the high power notch, and then 2 low level notches, and the notches are separated by quarter wave cables. The impedance in this point, with this well calibrated network analyzer, looks like this, and I can change the scale like that so I see better, and you can see that the marker 1 is a little bit away from 50 ohms because I have mistuned it. So now it's very close to 50 ohms. And the other one, I was tuning on the selective load, and marker 2 like that. So both are very close to 50 ohms. And for marker 2 I use this matchbox in front of the low noise amplifier. I have changed things since previous videos in that the inductances across crystals are made smaller. This way the notch is non-symmetric, so the attenuation is much lower 50 kHz below the center than 50 kHz above. Above the center there are false resonances anyway, so that range is not of any interest. The power level here is 26.4 dBm according to this instrument. This oscilloscope tells me that the voltage is 12.75 volts, and that is with a 50 ohm load on the oscilloscope input. This is 406 milliwatts. And this is another oscilloscope. It gives the same result, 12.8. And that's also with a 50 ohm load on the input. It's now connected to the normal test port, which is 50 ohms, and I'm checking the current with this current probe, and what I see is 250 millivolts, and that's 250 milliamps peak to peak. So the current is 88.4 milliamps RMS, 391 milliwatts or 25.9 dBm. Very close to 26.1 that I got from the voltage in 50 ohms. And the spectrum analyzer, I think they promise plus minus 1 dB, and it's 0.3 dB away from this and 0.4 dB from that. So I think power measurement is pretty accurate. I will be monitoring the power going into the test system here with this 20 dB coupler. And I'm looking at what is the output now from that coupler. It is plus 5.9 dBm. I have now connected this noise source. It is off now, and I have set the reading of the spectrum of Leningrad to show 0 dB on this scale. And now I switch it on. And I want to see a 3 dB increase on the noise, which I actually do at this level. And then the noise figure is 7.3 dB. It's on the... So it is much better than before, and that's because I changed the symmetry of the notches. This means a 3 dB increase of the noise. That is minus 166 dBm per hertz. When running the measurement with a straight-through wire, means this signal directly into here, I see obvious stability problems. This is something like minus 193 dBc per hertz. The instabilities are probably due to the connectors, so I will clean all the connectors and increase contact pressure where I think it's adequate to do that. The noise floor is well below minus 193 dBc per hertz, and that is with a straight-through wire. I now move to a series resonator with a ceramic capacitor, an old NP0. And this is more or less typical for a ceramic capacitor, a good ceramic. So I turn down the power level in steps of 1 dB. And I have to put back the lid on the box. I forgot that. Well, that wasn't the limitation. So it doesn't look perfectly stable. I now connect back to the straight-through wire. And you can see it is comparatively very quiet. So it is really the capacitor here that is the problem. And as you can see, it is now better. I increase the level. And I increase it very much. Then I go back. There seems to be some kind of memory effect. So I attenuate by 10 dB and then I go back. Well, I have set the attenuator to 12 decibels to get a noise floor in the neighborhood of minus 193 dBc per hertz. On the directional coupler, I read minus 8.5 dBm. Now I replaced that ceramic capacitor with a silver mica, 500 volt, and all the capacitors are 10 pf to give a resonance with this inductor in the neighborhood of 10 megahertz. The silvered mica is much better. It had some instability, and it still has, as you can see. But this is the full power that I can have. 0 and 0. And the level then is minus 3.7 on this spectrum analyzer. Now the silver mica is in place, and I will move the connectors between the straight-through wire and this LC resonator a couple of times. And it's quite clear. This is the straight-through wire, capacitor, wire, capacitor. So I can see the noise from the silver mica, and it varies with time. And here is the silvered mica, and here the straight-through wire. This is half an hour later, so the noise has went down a bit. The reason for the lower level is, of course, the attenuation in this LC resonator, which has losses to reduce the current significantly. This is an NP0 capacitor. I think it's from EPCOS. And it is very noisy. I put the lid on, and you can see the screen is entirely white, and I step in steps of 10 dB. 10, 20, 30. And now I can step 1 dB steps. Oops. Go for 10 more dB. So it's very noisy indeed. But here I have a noise floor in the order of 3 dB. We have 3 dB here. And on the attenuator I have to set 46, and the signal from the coupler is at minus 42 dBm approximately. It's a little bit noisy now. This is a ceramic NP0 capacitor, a pin-up capacitor from Philips. It's about 50 years old. And I have to set the attenuator to 10 and 0 to get the noise floor in the neighborhood of 3 dB. And the power level then is minus 6 dBm roughly. This is an NP0 ceramic that I bought from China about 20 years ago, or maybe 17 years ago, when doing the WSE converters. There are occasional noise bursts, but most of the time the noise is much lower than this minus 166.7 dBm per hertz that I have at 3 on the dB scale. But there are these noise bursts. So I connect instead the straight through wire, just to verify that the general system stability has not changed, at least not much. And again this Chinese capacitor, which often is very low but has noise bursts occasionally. The attenuator is at 0 and at 0, and the signal level is minus 0.5 dBm. And after a while it looks really good, with the noise floor only 1 dB above the noise floor at minus 166.7 dBm. So the added signal is far below that. This is another NP0 from Epcos. It's another batch. This one has 10P stamped on it. The other one had nothing on either side. To get the noise floor around 3 dB, like this, or a little bit below maybe, with occasional peaks significantly above. The attenuator is at can I see that? 11 dB, and the other one at 0. And the associated signal level is minus 8.8 or so. The noise floor is mostly below 3 dB, but I reduce attenuation by a single dB now, and then noise is significantly above 3. So I go back 1, 2 dB, and then it is very quiet. So there is a threshold for this capacitor at 7.7 on the 20 dB coupler. And this is a polystyrene capacitor, and I don't know from where I got it, but it's presumably very old. The attenuators on 0 and on 0, and the noise floor is a little below 3 dB, but with occasional noise bursts up to 3 dB. And the level here is plus 4.2 dBm. This is a 10 PF surface mount capacitor. It is this one, 10 PF, and it's from this box from Roderstein, and I have had it for more than 20 years. Attenuators, they are on 0. The noise is very low, about 1 dB only, and it varies, of course. And the signal level is minus 2.7. The level varies because the capacitors are different and they have a slightly different resonance frequency with the inductor. This is a high current ceramical capacitor. I have tuned the inductor, reduced the inductance a little bit in order to make the transmission through the LC resonator look like this. Because otherwise I wouldn't see any noise from this capacitor. The attenuators, they are on 0, and the noise floor I see is about 2 dB, and it's fairly steady, and the signal level is 4.2 plus 4.2. This is a plastic trimmer, and I tuned it for resonance. Maximum capacitance is 40 pF. The power at the directional coupler is plus 4 dBm, and the noise floor is stable at 2 dB. So this trimmer is a good capacitor. This is a ceramic trimmer, an old one, rated 7 to 45 pF. It is very noisy indeed. So here I have the standard noise floor at minus 167 dBm per hertz. Well, another dB. So the level at which this one gives this noise level, the signal level, is minus 47 dBm. Don't use this one in oscillators. This is an air dielectric trimmer, an old one. Air could not cause any noise, but there is a contact resistance problem because there is a movable contact when one is turning this thing. The air dielectric capacitor indeed has stability problems. So I have to reduce the level to something like this, and then suddenly it becomes stable. So I go up again, and now it's the full signal level. So this is, and here comes the instability again. So I think it will be fair to rate this one as something like, well, what do I see? 2 dB, and then 0 here, and then the power is 2.1 dBm. So instabilities show up at high currents through the capacitor. Now I'm running full power, and it is stable at 2 dB. And this is very good, as we would expect from an air dielectric. And the power level is 3.9 or maybe 4, plus 3.9 dBm. But it's unreliable. I knocked a little on the box here and got into this situation. So I attenuate by 10 dB, 20 dB, go back 10 dB, and go back 20 dB. Well, so there is some threshold at which this problem starts. Here. And that happens to be at what does it say? 5 and 0. So 5 dB attenuation, and then it becomes relatively safe. So this kind of capacitors, maybe they have a best before date. This one has been in my junk box for I think 30 years. This one is from Philips. I bought it in about 1968. I don't know what kind, if it is NP0 or something else. Ceramical tube capacitor, anyway. It is rather noisy, and I'm adjusting the attenuation to get noise level at about 3 dB. And of course, with this instability, the precise values become rather uncertain, but nevertheless, this is noisy, so it's not a capacitor to use for critical applications. I have set now, is it 4 dB here and 10 dB here, and the signal level is minus 12 dBm. 12 point, well, it varies quite a lot. So minus 12. Here is an NP0 surface mount from the Roderstein box. It is this one down here, and here I can see they are all NP0, so the one I tested before here was also NP0. Now I have tuned the coil to get a larger signal through the capacitor. Attenuators are on 0, and the signal level is plus 4.2. And the noise floor is stable at 2 dB. So it's questionable whether this capacitor produces any noise. Here are the results so far. I have computed the noise at 50 kilohertz below in dBc per hertz, and some capacitors are around minus 193. That means they haven't added any noise. Now, because they are in a resonant circuit, the power level at which this has been computed differs a little bit. The loss through the filter is here. So I could perhaps look a little bit more carefully at the silver mica, which had very large loss, and also this surface mount capacitor. But what is very important, I know the current through the capacitor, I can compute the voltage through the capacitor, and some have over 100 volts and don't add any noise even though the voltage is high. Some start to add noise already at 0.5 volt. And this is the NP0, the first one. And there is also one more, this one, the ceramic trimmer. Is really bad. 0.3 volts across it, and then the dBc per hertz is minus 140. And that's not much. These measurements are non-trivial. Suddenly I see an increased and a bit unstable noise floor. To investigate this, I use this notch filter here and insert it in front of the straight-through wire, like this. And indeed, the noise floor is much lower, and you can see here. So there is some error in front of this point. Now I have the notch on the oscillator, and the noise level is much higher. So there has to be a problem in this attenuator. I will try to replace it. So this is another. I leave the notch filter at 50 kHz offset in line to get a much cleaner signal. Then the noise floor is like this. If I read it here, 0.65 dB. This is the small surface mount capacitor from Roderstein, and I have tuned the inductor for minimum loss through this resonator. The noise floor I see is 1.8 dB. I'm testing the silvered mica again, but this time I have tuned the inductor properly. So this is what I see at the full signal level, and I apply attenuation to bring this down to about 3 dB. I have some problem with connections. But something like this. Attenuator is at 12 dB and 0. And the signal level minus 6.4. The silvered mica is unstable, however. This is at 12 dB attenuation, and sometimes there are noise bursts. Well, here comes one again. And if I now reduce the signal by 10 dB, I still see strong noise bursts. 10 more dB, and now the noise is very strong all the time. I'll try to read it out here. It's 17 dB, and that is at a signal level of minus 25 dBm. So not useful, this one. The conclusion is I found 5 good capacitors and many more that are not so good. So the good ones are the surface mount from Roderstein and the plastic trimmer and the ceramic power capacitor, and also a polystyrene capacitor. I hope this is readable, all of it. With the notch filter following the oscillator, the noise 50 kHz below the carrier is extremely low. Although the output impedance is not 50 ohms because there's no selective load on this notch frequency. Anyway, running it on the straight through connection in this box and with the attenuators set to 0 and 0, the noise floor I see is 0.53 dB. And I set very high attenuation to get the 50 ohm load. That is to check where the noise floor that is correctly calibrated. It's 0.0013 negative. And then I go back to 0 attenuation and look for the power. It's 6.8 dBm. Here are the details on the spreadsheet. The first column, noise increment, that is the S-meter reading. And then this is the attenuator setting. Here is the noise increase in linear power scale. It comes from 3.5 with this formula. And then here is the power that originates in the test object. And here it's converted to dBm per hertz with this formula. Go back to dB and subtract the room temperature and add the noise figure. Here is the power read from the directional coupler on the spectrum analyzer. And then the loss of the coupler is here. So this is the power coming out from the test object. And here compare that to the carrier power. And here is the power in milliwatts from dBm to milliwatts. And then I can compute the current coming out from the test object because I know the impedance is 50 ohms. Knowing the current through the capacitor, I can compute the voltage across the capacitor, knowing the impedance of 10 pF. And finally, here is the loss through the test object. Because of losses, in case it is properly tuned, otherwise it's mistuning losses also.